So on the agenda, I think this is the OFI architecture overview and mini tutorial or something like that. So I just call it a taste of OFI, Open Fabrics Interfaces. So what I mean by that is really when we're looking at, for this presentation, I did a selected analysis of what Open Fabric Interfaces is, the architecture, and the implementation. So I'm looking at just really different pieces of it. I'm not, obviously in 30 minutes I can't cover the full set of what this API can do. But hopefully by the end you at least get an idea of what OFI is trying to accomplish and how it's trying to get there. Okay, sorry, I don't use this version of PowerPoint, so what I see here is completely different. So to get into the architecture a little bit, I think it helps to back up and look at where Open Fabrics interfaces came from, how the working group came up with libfabric and OFI in the architecture. So obviously, as Paul mentioned, we started with a very rough conceptual model. And we took attack with that, created the OFIWIG the working group. One of the first things we did in the working group is we went through this large requirement analysis phase. We probably spent 3-4 months, with several weeks of gathering requirements from what does MPI really want from the API? What does PGAS, SHMEM want? I'm implementing sockets on top of it, a sockets API, such as extended sockets or RSockets. What features does that one of these APIs? We also heard from like the database management systems. Oracle came and spoke about what requirements they were looking for. So we gathered all these requirements. There's about 200 of them. We have a large spreadsheet that has the different requirements put in. We analyzed the requirements, and then we started a process of trying to design the API to meet these requirements. And this design process, this implementation has been very iterative. We've looked at what are the requirements the application's wanting. We designed the API. We started prototyping. We started writing MPI on top of OFI. We wrote SHMEM on top of OFI to see, do we have the right match? And what we're looking for is not only from the applications level, are we giving an interface that's aligned with them? We want to make sure if we get disjoint, then we're going to lose performance. But also from the other side, we want to make sure when we're creating these APIs that we're not just aligned with the application, that we're also aligned with the providers and the hardware underneath. Because if we get too disjoint from what the providers can do, again, we're going to suffer performance loss. So we want to try to make sure that we're aligned not just to what the hardware is capable of doing, but also what the applications want. We had a lot of collective feedback from the requirements and from OFIWIG. So there's probably been, I'd say weekly, there's 25 people or so who call into the OFIWIG meetings. So we've gotten a lot of feedback and a lot of input into how we need to design the APIs, what features we need, how to define those features so that they're usable to an application. So from the requirements, one of the first things we got back were one group of people who said, give us a very high-level interface. So my application, I don't want to have to implement a lot. Get it pretty close to what my application wants. Anything you need to do beneath, I don't care. And then we had another group of people who said, I want a low-level interface. Get it fairly close to the provider at the bottom side. And then let my application figure out how to use it. And the problem was this was the same group of people. So thank you, Jeff. So we had the MPI developers who said, I want high-level interface, and MPI developers who said, I want a low-level interface. And really, a lot of it comes from just the developer's preference or where they're coming from. For example, Intel has an MPI group. From their perspective, they would like to see something higher level that reduces their maintenance costs. But when you start looking at exascale, a lower level interface may be better. It lets you optimize more at the application level. And this fed into our design. So the design, basically what we did with the design, we kind of think of it as conceptually, we installed these two buttons into libfabric. We have the easy button that we borrowed from Staples, and then we have the advanced Guru button that the application can use when they want a low-level access. So from one viewpoint, the API is designed so that we can move functionality underneath these interfaces. And I have an example of that coming up in just a couple of slides. So if there's a feature an application requires, so the application absolutely needs this feature, then it needs to be implemented somewhere, whether it's in the application or whether we can push it down into OFI. And we want to at least enable the possibility that we can push some of these features down into OFI so we don't have every application having to implement it. Counter to that is we have applications that want very low-level access. They'll tell me what what the hardware does, and expose that to me and let me figure out the best way to use it. So we do have capabilities to be able to report really what are the resources that the hardware can provide. What are the capabilities that the provider needs? And I'll talk about some of those in just a couple slides too. So from the architecture, kind of view it in this format. We have these 4 different groups, the way I broke it up. And we have within each of these groups some collection of interfaces. You can think of this as kind of like an object-oriented model where these are classes. It's not quite implemented that way, but it may help to think of that way. So first we have these control services. The control services are discovery type APIs. This is really built around an application trying to figure out what's in my system. So not just what hardware is there, but what's the best way to use that hardware. So we have these APIs and these data structures I'll talk about that allow us to discover, an application to discover what's available in the system. We have some communication services. I won't go into detail on those in this presentation, but this gives you connection management. So if I want to connect to transport, gives me connect, listen. I also have address vectors. Address vectors are used for unreliable communication. Completion services, these are fairly standard. We just have event completion queues, and we also have counters for applications that need to know, I submitted 100 requests, I just need to know when all 100 are done. I don't need to know each individual one. And then we have some data transfer services. These are sets of APIs built around certain features or functionality that you want from communication. And I'll go into more detail on those in a couple slides as well. Okay. Sorry, just notice the clock on this laptop is off by a lot. Yes. So triggered operations, something we've defined, these are operations where the user wants to submit, they probably came from Oracle, they want to be able to submit a request, but they don't want that request to execute until some other event happens. So for example, they want to queue a message and say, I want this message to go out, but wait until I receive 100 RDMA operations. So I need to basically collect all the results from all my peers, and then I want to send a message letting them know that I have it. So starting out, we'll just push the easy button to see, I want a very easy way to use this. So what does that look like? If we look at the fabric information, back up just a second. So on this architecture, the first thing a user is going to come in contact with and what really controls these APIs, which interfaces they get, and the behavior of these interfaces is this down there in the corner of this FI info structure. So this data structure is what's used basically to query what's available and to configure the provider in terms of how you expect to use it. And 2 of the fields in that data structure, one, there's a field called endpoint type, and then there's a bit field called capabilities. And at a very simple level, an application can say, well, I want to communicate and I have 3 endpoint choices. So these choices came out, this is what the applications were asking for. So we had applications that want a reliable connection, we have applications that want datagram, and we have applications that want reliable unconnected, which we refer to as RDM, a reliable datagram message. And that follows socket syntax. So we have these 3 different endpoint types. An application that just wants to communicate, they want to just send receive data, they could just come up and say, I want just the MSG message endpoint type. That's all they need to do to request to get access to the Lib Fabric. Then we have various capabilities. So these 4 capabilities, how good your memory is, but these 4 capabilities were the 4 data transfer interfaces on the previous architecture slide. So we have 4 different data transfer types, and we can expand these. So again, this is extensible, so if we come up with a new way of moving data, we can define a new set of interfaces and expose that to the application. For example, maybe an active message interface might be appropriate to try to fit into this framework. So we have message queue, which is standard send receive messages. We have RMA, remote memory access, or RDMA. I should point out, in some cases, the naming that we chose was very specific, right? RMA, we're not trying to define that it has to be direct. We're just saying the user is going to submit an operation like an RDMA read operation, RMA read operation. The data is going to be fetched into the memory directly. How it gets there, we don't care. It may actually be through a data copy. Tagged messages. If you're not familiar with the tagged message interface, one way to think of its use is the receiver is going to associate some sort of tag with the buffer. And when the transmitter does a send, it's going to match those two tags in order to identify which receive that buffer is going to go into. So, simple example, the application posts two buffers, a 64K buffer and a 64-byte buffer. The 64K buffer, he writes the tag BIG. The 64-byte buffer, he writes the tag SMALL. When the sender does a transfer, he associates with his transfer a tag. That tag may be BIG. He may do a 16K transfer. At the receiver side, the receiver is basically simply indicating that if you get a message that has this tag BIG, put it in this first buffer, not the second. And then we have a fairly wide number of atomic operations that are defined within OFI and libfabric. And a lot of the atomic support's defined based on MPI requirements. So the application in the easy mode, simply come up and say, I want RDMN capabilities and I want message queue. They want to be able to just send receive messages, but they want it reliable and they want it unconnected. So I talked about what we want to try to enable is ways to push some functionality down under OFI. Well, imagine I have a provider that only does datagram message queue. For example, maybe the US NIC. So it does send receive messages, but it's not reliable. We want to be able to enable within OFI a module, for example, that can actually implement the reliability. So I'm not having every application have to add reliable transmit, retries, process acknowledgements into their application when they can just have a common implementation. And then we can optimize a single implementation. And this is defined such that when we have these modules, for example, this RDMN message queue common implementation, this module uses the exact same interfaces. So the module calls OFI itself and says, what do I have? And that module looks for, I want datagram messages, and I need datagram message queue. And he knows to implement reliability on top of it. So now when a higher level application calls OFI and says, I need RDM capabilities, this module can respond. So what do we have for the more advanced cases? So if you step back and look at, I mentioned the capabilities. We have these capability bits. I only mentioned 4. We probably have, I don't know, 15 or so different capability bits that are defined. And what the capabilities are really trying to look at is what are the features the application wants and what are the permissions. So some of the capabilities are, do I want to have remote memory writes into my local memory? Right, so that would be a capability where the application would want to specify, I want to be able to do RDMA operations and I want to be able to do reads and writes. So when we take the capabilities, we can split them into really 2 different categories. The first one, we have the primary and we have the secondary. The primary capabilities, and this is our advanced model here, the primary capabilities are ones that the application must specify to get. Most of these are because if the application did not specify it and you gave it to the application, it exposed the application to security violations possibly. If the application does not want RDMA operations, you don't want the provider to say, I'm going to give it to you anyways, and we're going to allow somebody to read and write into your memory. And then we have a set of secondary capabilities. These secondary capabilities, the application may still require, so they can request, say, I want this ability, I want this feature. Or if the application doesn't say anything about them, the provider can still turn it on. So this allows an application to say, I want these primary capabilities, but I know how to use these 2 secondary capabilities, which are usually used for optimizations. And this provider can give them to me, and I see those bits set, then it can take advantage of those in the implementation. So an example of a secondary capability. With most of the interface we've talked about so far, when we look at posting receive buffers, for example, most of the time with verbs, for example, you post a receive buffer, every receive that you post is consumed with one send operation. So you post a receive, a send comes in, it consumes the buffer, no matter what size the buffer. So if I post a bunch of 8K buffers and I get a 200-byte message coming in, I consume the full 8K buffer. So from this API, a lot of the requirements we got were, I want to be able to say, I want to give you a big buffer. Here's a megabyte worth of data. Just pack the receives in as tightly as you can. So we have a capability bit that indicates whether or not the provider can do that. So the provider, we call it multi-receive. So if multi-receive capability is set, that means the provider can say, here's one big buffer. The receives will just pack in there. He doesn't have to call post-receive, post-receive. He has more efficient use of the buffer in that case. So this is a feature that if an application checks for, they can take advantage of. And the provider can automatically set, even if the provider doesn't ask for it. The provider can just say, you have it if you want it. And there's probably 3 or 4 of those types of capabilities. In addition to those, in the FI infrastructure, we have various attributes. The attributes are defined in terms of really what are the limits of using the interface and what's the behavior the application's expecting. So limits are common things like, number of entries in a queue. So how many send operations can you do? How many receives can you post? That sort of stuff is just a limitation on, if you go beyond this, then the expected behavior is that the API is going to fail your request. And for the behavior, I've got some examples coming up in a few slides as to what those sort of attributes look like. And the last one we have are mode bits. Mode bits is when we looked at this, again, we're trying to make sure we're aligned with the application to the OFI. We want to make sure we align OFI with the provider. And we found that there's certain features the applications simply want, and there's certain things providers want the applications to do in order to keep that alignment. So we have mode bits that help us keep the alignment between OFI and the provider from being disjoint. And I have some examples of those as well. So some of the additional attributes, these are the behavior options. Question?
Sorry, in the previous slide, we talked about features and conditions. I understand if you want to think of a feature, you're going to have to conditions, I didn't get that.
So there are some, question is, are the permissions related to the capabilities? There are some capability bits that are related to permissions. An example I think I gave was whether or not you want to enable your endpoint for RDMA write capability or RDMA read capability. So back up here, there's a capability bit that says I want to have RMA support or I want to have atomic support. Right, so the endpoint saying I want to be able to do RMA, we allow additional capability bits to be set to indicate what type of RMA are you wanting. If the application puts nothing, they get read and write capabilities. But they can restrict saying, I want RMA, but I only want write access.
So it's sort of modifying your feature.
Correct. Right. Again, this is a more advanced model where normal application could just say, I want RMA, I don't care. But if they want to have additional selection control, they can say, I want atomics, but I want to be able to initiate it. I don't want somebody to send atomics to me. I just want to be able to write to somebody else.
Right. And the easy versus the guru selection, is it literally a bid in FI input, or you're just saying the same interface can be used 2 ways?
It's the same, and it's a range. So I can use certain things easy in a more easy mode, certain things in a more advanced mode. So there's no bid. I'm just making that up so I have a thing to put on my slide. So for the threading options, in one of the behaviors, this is looking at, is synchronization needed? And we actually iterated over this quite a while on OFIWIG, and what we ended up with was, in the easy mode, simply you say the interface is thread safe. So if an application says, my attribute, I want it to be completely thread safe, or they don't put anything, then we can provider can return saying, I can give you thread safe access. So now a multi-thread application just works. And then we have a capability where we have a way to communicate between the provider and the application how resources can be used so that no locking is required, no synchronization is required. For example, in this case, say if you take your endpoints and your completion queues, any endpoints associated with any completion queue, put it in the same set. So I have in one case, endpoint 1, CQ1, that's in the same set. Endpoint 1's completions go to CQ1. Now in another set I have endpoint 2, its completions go to CQ2 and 3. And that has another set. As long as these two sets are fully disjoint, I don't need to have threads synchronized to use them. I can have thread 1 access endpoint 1 CQ1 with no synchronization. I can have thread 2 access endpoint 2 CQs 2 and 3 with no synchronization. So we're simply trying to identify what collection of resources can an application access without locking as long as the application only accesses those resources from one thread, or the application does their own synchronization. So the application in this case cannot have thread 1 access endpoint 1 and CQ1 at the same time, for example. You can't have two threads going into that endpoint and that CQ at the same time. And we have a set of attributes defined for what sort of threading model is being employed. Progress, as mentioned, this whole design, again, it's implementation. Paul called it transport agnostic. It's really trying to be implementation agnostic. We're not trying to define how the hardware or how the provider implements anything. It may be fully offloaded into hardware. It may be a combination of hardware and software. It may be full software model. So the progress mode, we have two different progress modes. The easy one is automatic. The application submits a request. It just completes. And this would be what you would have, for example, if you had a fully offloaded model. So they do a send request. The application goes to sleep for 9 minutes. They hit wake up from the snooze button. They check the request. It's done. They haven't done anything in the process. The manual mode, this allows an application, basically the provider is saying, I'm going to use your thread to complete the request. So if you want automatic, so we make all providers support automatic, but we allow the providers to indicate that if you want automatic, there's going to be a performance penalty. It would be better for your application if you can handle a manual mode of progress. In this case, the applications or the provider is going to steal the application thread to complete requests. So in that easy example I gave where I took the RDM module and moved it down underneath OFI, what's doing the transmits and the retries? I implemented this module, the application is sending a request, underlying hardware is just doing datagram, so something's doing retransmissions, looking for acknowledgements. Do I have an extra thread for that? Or am I simply grabbing the application's thread when he drops down beneath the library to process those timeouts? And this progress mode allows us to report this back. So this is where you could actually have kind of that mixed, easy, advanced mode of operation. Resource management. This is looking at flow control and also how you access local and remote queues. So we define, and there's a lot of variation we could define here. We define simply two modes, either it's enabled or disabled. If resource management is enabled, what that means is that if the application tries to submit a request and there's no space in the local send queue, for example, it gets rejected. The application sees E again. In addition to that, the provider is also required, so if you submit a request and that request could overflow the completion queue, fail the request. So now we know the application is going to be protected against overrunning the transmit queue. They're going to be protected from overrunning a local completion queue. If there's no buffer on the remote side, we expect some sort of flow control to take advantage of it, or to be employed, which means I don't do the send and I overflow and break the connection. So if I have no buffer at the remote side, flow control should kick that send back and be retried automatically by the provider, usually through hardware. So this would make, for example, R&R and ACKs. In addition, if we don't want to overrun the remote, not just receive buffers, but remote receive queue. So when resource management is enabled, basically we're looking at this full spectrum from the transmit to the receive to the completion on both sides. The provider is responsible for ensuring that there is no overruns of those queues. Otherwise, the request doesn't ever get accepted by the provider to begin with. If this is disabled, the application say, I'll manage this myself. If it's disabled, then the provider is free from having to do those checks. And notice in this that when we're defining these sort of capabilities or these attributes, these are the behaviors that the application can rely on. So if the application does disable on resource management, they need to expect that they will get no help from the underlying provider. From the provider's viewpoint, there's certain requirements the provider must meet, and then there's potential optimizations, right? But there's not restrictions. Just because the resource management's been disabled, the threading's been turned to manual, doesn't mean the provider has to disable everything. For example, R&R retries may be built into the transport protocol. You may not be able to disable flow control. That's okay. So the provider that meets the enabled case automatically meets the disabled case. Same thing with the threading model. If the provider meets the automatic threading model, they automatically meet the manual threading model, just by the definition that they're used. So they're looking at just, as a provider, you have the chance to optimize in this way.
question.
For data ordering, question?
So does that mean that all providers have to implement Easy to be valid?
There are certain requirements that we have defined in the interface as to what the providers need to meet. I don't know if we have one defined for like resource management. For threading, we do. We have a requirement that you have to support the automatic threading model, for example. For data ordering, obviously this is, if the application submits different requests and their completion, what order are the requests processed, what order do the completions show up in. So we have an ordering model where, call it strict, that says the requests are processed in order. The user submits 10 requests, they'll probably be processed in order, they'll complete in order. But we also have more relaxed ordering modes. And the ordering mode is basically a series of bits. It's not as simple as selecting a value from an enum. But the ordering allows the application to indicate where ordering is required and where ordering is not. For example, if they have an endpoint and they want to do RDMA read operations, RDMA write operations, message sends, that they can say, my message sends and my RDMA operations don't have to be ordered. I don't care what ordering that's in on. Or maybe that he can say, I want to have my messages, I don't want any ordering on my messages. I don't care how they're delivered. If there's any ordering that's required, the application is going to take care of it. And this basically allows the provider the chance to optimize. He can use dynamic routing. If he has multiple ports underneath, he can now stripe the data across multiple ports. Whatever the provider wants to do to try to improve performance, the provider has that freedom now. All from the application's viewpoint, you're saying, I'm not dealing with ordering. You can optimize however you want as the underlying provider. And now mode bits. So for the mode bits, I mentioned these are hints from the provider up to the application in terms of what's the best way to use this provider. Mode bits really represent things applications don't want to do. So when you go through the requirements of what applications want, none of the applications are saying, I want to do this. Applications are saying, I don't want to do this. But we want to provide a way for the provider to indicate up, if you do this, life will be much better for you. So I have 3 examples here. Just pick the second one. So we mentioned kind of the progress mode. This manual progress mode where the provider is going to steal the application thread to do transmits and retries. The context mode bit indicates that the provider wants the application to give it scratch space. So when the provider submits a request, if he gives him a small amount of scratch space, that allows the provider to track the request, for example, to set the timeouts, to check for the retries, and then process the completion. And what this alleviates is the provider from having, for example, when the request is submitted, from going and having to pull some data structure off of a queue. So if the application can just give me this small amount of space, that saves me from having to do this queue lookup and synchronizing access to that queue inside the provider. So that's a case where applications don't want to do this, but it can improve performance if they do. And you can see how something like that could tie back, for example, to this RDM common module. You submit the request to this common module, and he wants to sit there and do retries. Well, that means he's got to track the request somewhere. In order to track the request, he needs some sort of data structure to do it. But that data structure may be small. If the provider can just give him this context, then he's fine. And it turns out a lot of applications can do this without a huge penalty because the applications themselves already have to track the requests. So I just have 3 more slides that are fairly quick. So back to the architecture. So once we've configured all this, now we have these data transfer services. I'm going to talk very quickly about the data transfer services. So I mentioned the endpoint case. In the easy case, the application allocates an endpoint. You can think of an endpoint as a socket, a queue pair, whatever we call it. But basically, it's some sort of addressable communication portal concept object. The application gets an endpoint. In the easy mode, the endpoint has transmit queues. It has receive queues. You post sends receives. They go to these queues. Completions go over to some completion queue. So that works the same as it always has. Taking that a little bit further, we may have restrictions on the hardware, for example. Maybe the provider says, I can give you 10,000 endpoints, but I only have room in my hardware to actually operate 100 successfully at any one time. We want to provide a way through these attributes to indicate that to a resource manager. So a resource manager can look at it and say, hey, I can only actually run 100 of these transmit queues at a time. So we have this concept of shared transmit and shared receive context. And I call them context instead of queues because they may not be processed in order. The ordering may be changed based on what the application said. So now my endpoints can share the same transmits, the same receive queues, and this gives the resource manager better control over, if I only have 100 of these, but I'm going to allocate 10,000 endpoints, well, I can allocate 50 endpoints that have their own transmit queues, because I need those 50 to be fast, and I can have 50 share the other 900 or 9,950, whatever I said. Going the other way, we have the concept of scalable endpoints. So scalable endpoints has a single endpoint with multiple transmit queues or multiple receive queues. Now, the mix between shared and scalable, they're not disjoint. You can actually have shared on one side and scalable on the other. So this is where you have a single endpoint where you have maybe 4 transmit queues. So rather than having 4 endpoints, I have 1. And the advantage of that is I've reduced the addressing. So rather than having to record 4 addresses for every guy I'm talking to, I just record 1 address. Because I have this 1 endpoint address. And now I can have the data go out different transmit queues. And I can use the different transmit queues, for example, to take advantage of multi-threading, for ordering, how I'm handling progress or direct completions. And then also on the receive side, same thing. When I have data coming in, I can have the data go flow to different receive queues. Maybe those are assigned to different cores on the processor, or maybe those go to different completion queues. And then we also have an option, maybe I can let the sender, when he does a transmit, indicate which of those receive queues he's actually wanting to go to through some sort of indexing scheme. So I had an early cut point, so this is my early cut point. So OFI really is trying to give you the capability of having an easy implementation where you want it, but it's also trying to give you the ability to have very low-level access where it's wanted. And it tries to do this in a very agnostic way. It doesn't care what the implementation does. It tries to abstract all this hardware. And again, we analyze this across multiple vendors' hardware. Probably 4 or 5 different non-verb type devices and 3 or 4 verb devices to make sure that we can map this very well against non-verb hardware and against verb hardware, and that these interfaces would align well in all those situations. Yep. I'll stop there because I'm out of time.